Okay, some final comments on exponential smoothing, some practical concerns. First, data. We talked about this briefly, but I think it's very important to re-emphasize the fact you need 3 different data sets. You should strive to have 3 different data sets. The first, to estimate any of the parameters, the level, the trend, or the seasonality factors. And again, if I suspect some kind of seasonality, I need multiple seasons. And in fact, I don't know how you're going to even try to see if there is seasonality unless you have multiple seasons there. Then you want a set of data to train to determine the smoothing parameters. And then finally, once you have those, you want to take a new set of data, or a later set of data, and evaluate the quality, the accuracy, and the bias of the forecasts, and just see how well it does. Try to avoid initializing, training, and testing on the exact same data set. Okay, how do I select the data to be used in the model formulation? Well, this is what caused the problem. There's a trade-off. So I want it to be as long as possible, but it still has to be relevant. And you also want to clean out these non-repeating events. One of the common problems that can happen is that a promotion was run in a previous period, let's say, and it was left in the exponential smoothing model for history going forward. Then what's going to happen is you're going to use that promotion, which usually peaked sales. You're going to see this peak in demand and expect it to happen again next year when it might have been a one-off. So you want to remove all promotions. And in fact, when we talk about causal analysis, we'll talk about maybe you want to measure the effect of a promotion, and therefore you are able to build in the expected demand if you're going to run a promotion, because that's a very powerful tool. But you need to make sure that the data you're using for history is really history, and you've removed those non-repeating events like promotions and things. Okay, appropriate smoothing factors. No hard and fast rules here, just some recommendations from different sources. Level, I would pick the alpha smoothing parameter between 0.01 to 0.3. 0.1 is reasonable. If it's part of a larger model like a Holt-Winter where you have trend and seasonality, you might want to ramp it up a little bit. 0.19 is reasonable, but you can tweak around and see what this does. For the betas, anything between 0.005 and 0.176. And then you see the gamma for seasonality. A good range is from 0.05 to 0.5, with a 0.1 is reasonable. Now, suppose you were bad and you use the exact same data to initialize and to train your data. And what you're trying to do is find the best alpha, beta, and gamma to minimize your sum of squares, your mean square error. So I'm trying to find the best ones to get the best fit. Chances are your alpha is going to be very high, your beta is going to be very high, your gamma, it could be all over the place. It depends. Why? Because what you're doing is you're finding the best level alpha and the best trend smoothing factor beta that fits as best as possible to that data. And so you're going to create estimates that are very nervous. They're going to be fast following. And so those very volatile parameters, remember, I'm valuing my new information a lot more. Chances are when you test those in another data set, they'll do quite poorly. So you have to worry about overfitting. The natural tendency of students or people new to forecasting is to ramp up the alpha and the beta factors because it looks like it fits the goodness of fit to the curve, and it does. But remember, the purpose of the model is to forecast going forward, not to best fit history. Okay, a couple more things. Most of the work, as you probably saw, and if you did the problems, is bookkeeping. You just got to keep track of stuff, especially when you get to the Holt-Winter model. You have a lot of seasonality indices that you have to keep normalizing and updating. And after a while, you see the mechanics of it. But that's why I wanted to go through a bunch of examples so you get to see and get a handle of the mechanics. It's a lot of rote. So the initialization procedures can be somewhat arbitrary. You're kind of finding an average and doing the best guess. But as the forecast progresses, those initial estimates will eventually wash out. And again, seasonality, while it makes sense, it's almost always there, boy, it greatly complicates a lot of what you have to do. One thing you should always look to do is measure your ongoing bias in your forecasts. So a way to do this is just to keep a sum, a running cumulative sum of your errors, of your absolute errors. So you just keep summing up in here. I have that this C sub t is equal to C sub t minus 1, the last periods, plus the new error term. And I can normalize this by dividing by the square root of the mean square error that I just estimated. And what that does, that gives me a more normalized number. But the important thing is you should fluctuate around 0, right? This number, right, if here's 0, you should be, if I'm normalizing it, hopefully you're going something like this. If you find that you're trending way up or trending way down, then you've got a bias problem. So this is a good thing to track and to keep track of going on. Okay, so we talked about a lot of models, but we barely scratched the surface of what's out there. Forecasting is its own domain. This you can do a whole course, series of courses, get a whole degree in econometrics that can be used for demand modeling and forecasting. So what I'm showing in this table below is what can be done for exponential smoothing and where the models that we've done fit in. So we looked at seasonality. You can have a model that has no seasonality, additive seasonality, or multiplicative seasonality. You can think of the same thing for the trend. You can have no trend if you assume that in the model. You can have additive trend or multiplicative trend. You can have dampening of trends. It can be there or not. Remember, that's where the trend tapers out over time. So what I have here is a simple chart where the columns are the seasonality components. Again, none, additive, and multiplicative. And the rows are the different trend components, the different ways that we can measure the trend. We assume you always do level. So here there's no trend, we have an additive trend, an additive damped, multiplicative and multiplicative damped. And you can see where the models fit in that we looked at. We looked at 5 different models: the simple exponential smoothing, which is just a level, no trend, no seasonality. Then we looked at the Holt model, which is an additive trend, no seasonality, with a level. Then we looked at the damped Holt, where all we did was dampen the trend component. Then we introduced the double exponential smoothing, which had a level, no trend, but had multiplicative seasonality. And then we did Holt-Winter. But look at all these open ones that we didn't look at. So there's a whole bunch of other combinations and models and that you can go for. There's also some other types of modeling that you can look at, and probably the most common one that we're not going to talk about, but it's worth exploring if you're interested in this to go further, the Box-Jenkins or autoregressive integrated moving average, ARIMA. You'll see a lot into this. If you're interested in this area, that's probably a good next step for you to dive in. All right, so that's all we're going to talk about for exponential smoothing. Hopefully, if you have any questions, comments, or suggestions, you'll use the discussion. You won't be confused like Ginger Bell. You'll use the discussion and help you solve your problems.